Welcome to the second lecture on the category of vector spaces titled Vector Spaces. Let's review a few points from our previous lecture. A vector space is an abstraction of the set of vectors of the plane together with its addition and scalar multiplication. The addition of vectors of the plane endow the set of vectors with the structure of an abelian group. A group is a set endowed with a single binary operation satisfying three conditions. The operation is associative, it admits a neutral element which is necessarily unique, and every element of the group has an inverse for this operation, again necessarily unique. An abelian group is a group whose operation is commutative. To define the scalar multiplication of vectors, we introduce the structure of a field, which abstracts the algebraic properties of the field R of real numbers. Let us now introduce the objects of the category of vector spaces. A vector space V plus dot over a field K is a set V endowed with two binary operations: an addition from V times V to V, and a scalar multiplication from K times V to V, with the following properties. First, V with the addition is an abelian group with neutral element denoted by 0. I remind you that abelian group means plus is associative, there exists a neutral element called 0, every element of the vector has opposites for the addition, and the addition is commutative. In addition, I require distributivity of the scalar multiplication with respect to the addition, that is for all lambda in the field K, and for all x and y in V, lambda times x plus y equals to lambda x plus lambda y. Now the field K has its own operations, an addition and a multiplication, and we want some compatibility between the operations on K and the operation on our vector space V. First, we require that for all lambda and mu in the field K, and for all x in V, the sum of lambda and mu times x is equal to the sum of lambda x and mu x. It's a form of distributivity. Second, we ask that for any lambda and mu in K, and for any x in V, the product of lambda mu times x is equal to lambda times mu times x. Now, I've used the word times only to refer to the scalar multiplication in that particular identity. It is a form of associativity, but pay attention that we multiply lambda and mu in the field K on the left-hand side, whereas we do not involve the multiplication of the field K on the right-hand side. Last, to avoid degeneracies, we require that for all x in V, 1 times x is x, where 1 is the unit of the field K. This is the main structure we are going to study in linear algebra. Elements of a vector space over a field K are called vectors. So, a vector is simply an element of a vector space. On the other hand, elements of the field K here are going to be called scalars. Let us see some examples of vector spaces. Maybe the simplest example is that any field K is a vector space over itself. After all, K for its addition is an abelian group by definition of a field. The definition of a field also includes left distributivity. We proved in our first lecture that we also have right distributivity in a field. Thus, the first compatibility relation in the definition of a vector space must hold. The multiplication of a field is associative. We also proved that in our first lecture. Thus, the second compatibility relation in the definition of a vector space also holds. And last, by definition of the unit of a field, for any x in K, what 1 times x is indeed x. So here we have it. Any field is a vector space over itself. There is another example, which is maybe even simpler. If you take any vector space, for instance, K, a field, and you simply take the singleton consisting of the neutral element for the addition, the vector 0, then this is a vector space essentially trivially. What is important here is to note that a vector space, being in particular a group for its addition, cannot be empty because it must contain at a minimum a neutral element for the addition. So the singleton 0 here is basically the smallest vector space we can possibly have. Let's now look at more complicated examples, namely what I call the fundamental example, function spaces. I call those examples fundamental for two reasons. The first is a personal bias. Since I'm a functional analyst, I study a lot of infinite dimensional vector spaces which are given as function spaces. It is a very vast set of application of this theory we are working on right now. But second of all, we will prove in a few lectures from now that in fact any vector space is a subspace, in a sense to be defined in the next lecture, of one of those function spaces. So any vector space we look at could be in fact seen as living inside one of those function spaces I will now define. This will give us a lot of new examples. I'm going to take a non-empty set called D. D is meant here for domain, and it can be any non-empty set. It needs to have no structure. I'm also going to take a vector space V over a certain field K. So in particular, V could be K itself, but V could be one of the vector space we are just now going to construct. So I'm going to take two functions from D to V, call them f and g. And I would like to know what it means to add f to g. Well, if I take an element x in the domain D, then f of x and g of x both are elements of the vector space V. Therefore, their sum is well defined. Since I can do that for any x in D, I can indeed define a function from D to V by this bullet point 1, which is the pointwise addition of the function f and the function g. Similarly, for any scalar lambda and any function from D to V, I can define lambda times that function by multiplying for every x the image of x by that function, which is a vector in V, by the scalar lambda. This is well defined as V is a vector space over K. I claim that the set of functions from D to V with the addition and the scalar multiplication is indeed a vector space over K. Let's prove that. First, the set of functions from D to V with the addition is an abelian group. I need to check that the addition is associative. That is, I need to check the identity that is at the bottom of this blue box. I take three functions from D to V, f, g, and h, and I take an arbitrary element x in D. Since f of x, g of x, and h of x are all three elements of V, which is a vector space, and in particular, therefore, V plus is an abelian group, we know that plus, the addition on V, is associative, so f of x plus g of x, parenthesis, added to h of x, is equal to f of x plus, parenthesis, g of x plus h of x. That's just associativity in V. Since this is true for all x, however, I can indeed conclude that the addition on the functions is also associative. Now let's prove that the addition that we have defined is commutative. You take two functions from D to V and call f and g, and let's take an arbitrary element x in the domain D. Again, since the vector space is in particular an abelian group for the addition, we conclude that f of x plus g of x is equal to g of x plus f of x, since g of x and f of x are elements of V. But since this is true for an arbitrary element x in my domain, I have indeed proven that the addition of function is commutative. We need a neutral element for this addition. There is a natural candidate, which is a constant function on D equal to the 0 vector in V. I call that bold 0 to distinguish it from the 0 of V in this little slide, but as you know, in general, we just would use the notation 0 for that function as well. Now, if you take any functions from D to V, and you calculate f plus that 0 function using the definition of what addition means, what it means is that for any x in the domain, I need to calculate f of x plus 0 in the vector space V, where that is in fact f of x because 0 is neutral for the addition. So f plus the constant function equal to 0 is indeed the function f. 0 is neutral for the addition. Last, in a very similar way, if I give you a function from D to V, I need to find an opposite for that function and for the addition of function I have defined. Well, what I'm going to do is I'm going to set minus f to be the function that to any x in D maps to the opposite of f of x. F of x is a vector in V, so it has an opposite for the addition. It is just a matter of checking that f plus the opposite of f in the sense of bullet point 1 in the green box above is indeed equal to the constant function 0, my neutral element for the addition. So I have shown that the set of functions from D to V with this particular addition is indeed an abelian group. These are the other properties I would need to check, distributivity and the three compatibility relations. They are proven in the same manner as what we have just done to prove that V, the set of function from D to V with the addition, is an abelian group. It's the same proof, same sort of argument, so I'll let you practice on it. Here's another way we can fabricate new vector spaces from old ones. Suppose we have two vector spaces. Now we have already quite a rich source of vector spaces. Of course, we have the field in the singleton 0, but we also have functions from any set you want into the field, and then functions from any set you want to the set of functions from some set to the field, etc., etc. So we have a lot of vector spaces already, but say take any two of those, and I'm going to endow their Cartesian product V times W with the structure of a vector space. So V and W are two vector spaces over the same field K, and if we define an addition and a scalar multiplication essentially coordinate-wise, as written on the slide, so for instance, if you take V1, W1 and V2, W2, two elements right now of V times W, then I define their sum as the ordered pair V1 plus V2, where I added those vectors in V, and W1 plus W2, where I added those vectors in W, and similarly with a scalar multiplication, then I claim that the resulting object is again a vector space over K. We're going to look at some element of the proof. So first you want to prove that this addition I have defined is associative. You need to take three vectors in V cross W, and we need to calculate the sum of the two, then added to the third. So this is what's written here. So when you do that, well, you first actually use the plus on the first pair because the parentheses tell you to do so. You then add the third pair. Then you use the fact that in V, the addition is associative. So the sum of V1 and V2 added to V3 is the same thing as V1 added to the sum of V2 and V3. We do the same thing because the addition of W is associative on the second component of this ordered pair. We move the parentheses to the right. Then we sort of unwind what we did. We recognize that this expression here is the first pair, V1, W1, added to the sum of the two other pairs. And thus we have proven our associativity. All other properties are proven similarly. So let's just see, look at maybe a couple of others. First, we need a neutral element for V cross W. Well, there is a 0 in V and there is a 0 in W. We use the same notation for them, but they are a priori completely different elements of different sets, but they both are neutral elements for their respective addition. So you make the pair 0, 0, and it's easy to check that it is neutral for the addition. Another idea is, well, if I take a pair in V cross W, call it little v, little w, I want an opposite for this, for my addition. What should the opposite be? Well, V has an opposite in V because V is a vector space. W has an opposite in W because W is a vector space. Let's take those two, form the ordered pair minus V minus W with our usual notation, and you check very easily that by definition of the addition, the pair VW plus the pair minus V minus W is indeed equal to the neutral element 0, 0. The other properties are established in a similar fashion. So, this is another way to construct vector spaces by taking the Cartesian product of two spaces. I'm going to look at a special application of this result. If I take a vector space V fixed once and for all, and some natural number that's not 0, then I can form the Cartesian product of V with itself d times. And I can define those two operations listed here between d tuples of V to the d and scalars. What's interesting here is that this is simply a special case of the previous slide, right? Because V to the d by induction is V cross or times V to the d minus 1, and you repeat that, d times. So V to the d is simply, by induction, a vector space using the proof we have already made. Okay? And in particular, this applies when V is a simple vector space of the field itself. So K to the d, with the addition and this scalar multiplication on this slide, is an example of a vector space over K. So in particular, say R to the d or C to the d are vector spaces over respectively R and C. There would be another way to see that this structure here is indeed a vector space. It's a little exercise I leave you to think about, to play a bit with all these notations and concepts. Note that if you take a function which goes from the set 1, 2, 3, etc. d to the vector space V, then I can associate to this function in a rather canonical way an element of the Cartesian product V to the d, namely f of 1, f of 2, f of 3, etc. f of d. So I call for a function f from the set 1, 2, etc. to d to v, I call this image d tuple theta of f. Then we define a map, theta. And then map I claim is a bijection, and it intertwines the addition and scalar multiplications that we define on the one hand on the function space of the functions from 1, 2, 3, etc. to v, and on the other hand, the operation I define on vd just in this green box right here. And it turns out that we can make a little exercise where you can check that since we know that the function space is indeed a vector space, the fact that theta is a bijection, that is a morphism for both the addition and the multiplication, scalar multiplication here, that forces indeed V to the d to be a vector space. It's a little bit more complicated than doing it straight by hand, arguably, but at the same time, it's also very interesting because we really see that this example we are looking at right now is just a special case of a function space. I should say, though, that in general we can take the product of arbitrarily many vector spaces. Now, when you do that, the definition of addition and scalar multiplication are very similar to the finite case. They are component-wise addition and component-wise scalar multiplication. It is important, of course, that all the vector spaces are over the same field K. So when the set J in this notation here, the index set J that I use in this theorem is reduced to a two-point set, and you have two vector spaces. This theorem will give me the same construction as we did 2 slides ago about product of 2 vector spaces. The same generalized to an arbitrary family. The proof is actually quite similar to the proof that the function spaces are indeed vector spaces, but it is not the same. In fact, technically, this theorem here is slightly more general. but the techniques for proving it are exactly the same, so I will leave you to check all the properties that this arbitrary Cartesian product is indeed a vector space over K. I'm now going to turn, like we did in the first lecture, to some basic algebraic properties about vector spaces, so that I can do some calculations and use some basic results that are not assumed but derive immediately from the assumptions of what a vector space is. So the first property I'm going to do is to prove that if V is a vector space, and I take any vector in V, and I multiply it by the 0 in the field K, then I get the vector 0. 0 times x is always 0. Careful, the 0 on the left-hand side is a 0 in the field K, the 0 on the right-hand side is a 0 vector in V. The proof is going to be similar to what we saw when we were working with fields. As V with the addition is a group, we know that for all x, y, and z in V, x plus y equals x plus z must imply that in fact y equals z. This was the first proof of the first lecture. So let's try to use this to prove our result. Let's calculate 0x plus 0. Because 0 is neutral in K for the addition, this is equal to 0 plus 0 times x plus still 0. But then I can use the distributivity for the external or scalar multiplication with respect to the addition. This is equal to 0 times x plus 0 times x, still plus my 0 that I have done nothing with so far. Well, in fact, I've done so little, I'm going to drop it. After all, adding 0 to anything in my vector space, by definition of what 0 means here, it's a neutral element for the addition. It does nothing. So I get this equality. 0 times x plus 0 is equal to 0 times x plus 0 times x. But if you look at the equation right above this, you can deduce from that 0 times x must indeed be equal to 0 by cancelling the other 0 times x. So, multiplying a vector by 0 gives you the 0 vector. This is a reassuring news, and we have proven that using only our definition of a vector space. Here's another basic algebraic property which should be a little bit familiar from our work with fields. If V is a vector space, then for all x in V, minus 1 times x is indeed minus x. I remind you, minus x here is the opposite of x in the abelian group of the vector space V with its addition. It has nothing to do with the scalar multiplication, at least on the surface, because we're actually going to prove it does have to do with the scalar multiplication, in that you could also calculate minus x, the opposite of x, by multiplying x with the scalar minus 1, that is with the opposite of 1 in the field K. This connects those two structures. So, once we have understood this notation here, the proof is going as follows. We calculate minus 1 times x plus x. We assumed as part of our definition of a vector space that 1 times x is always equal to x for any vector x. This was this last compatibility property. So, minus 1 times x plus x is equal to minus 1 times x plus 1 times x, because x equals 1 times x. Now I can use the distributivity of the scalar multiplication with respect to addition, and I get a sort of factorization, if you want, that minus 1 times x plus x is now equal to 1 plus minus 1 in the field times x. Well, the sum of 1 and minus 1 in the field is 0. That's the definition of minus 1. And therefore we have shown that minus 1 times x plus x is equal to 0 times x, which we have proven on the previous slide is 0. Now, the addition is abelian, so we have it both ways. And we prove that in a group, the inverse is unique. So minus 1 times x must indeed be equal to minus x. Now, I feel a little less guilty to introduce a notation for the difference of two vectors. X minus y for vectors x and y in a vector space will be meant for, well, your choice, x plus the opposite of y. That would be the natural definition. But it's also meant for x plus minus 1 times y. There is no ambiguity anymore because, in fact, we have just shown that minus y is equal to minus y minus 1 times y, and therefore these two, of course, two quantities are the same. So now there is no risk of confusion, and we can happily talk about differences. I want to point out, however, there is a little bit of genius in the idea of working with addition and opposite rather than with differences. You saw that we have nice properties about the addition. It's associative and so on and so forth. Well, the subtraction as an operation is not quite as nice. In particular, you should check that it is not associative. So it turns out that it is a lot easier to work with only the addition and invoke opposites or inverses whenever you want to do the subtraction. This is an interesting observation that algebraists made a long time ago, and that has proven to be extremely useful. So this difference here, I mean, it is a new operation, but I'm really looking at it as just a notation. Because as an operation, it doesn't have really nice patterns. So it's just a way to simplify my notations when I need to, not much more. I will now give you two exercises, which are in the same vein as what we have done so far, to prove two new relations or two new properties of the algebra underlying a vector space. I suggest you pause the video, as I will actually go over the solutions for these two problems in the next slide. So let's prove these two little properties in vector spaces. Let V be a vector space over a field K. First, I want to prove that if I take any scalar lambda, lambda times the zero vector is again the zero vector. Do not confuse that with the properties we just proved before the exercises, which was that if we have any vector x, multiplying that vector by the scalar 0 give me 0. It's kind of the other way around. Here the vector is always null, but we can multiply it by any scalar and we still get the null vector. All right. So the proof is a bit similar, of course. So if you take your scalar lambda, lambda times 0 vector, which by the way is lambda times 0 plus 0, because adding the 0 vector does nothing. Lambda times the 0 vector is equal to lambda times the 0 vector plus itself, because 0 is neutral. So 0 plus 0 is equal to 0. Again, we can use distributivity to get that this is equal to lambda times 0 plus lambda times 0. But in that case, we have proven again that lambda 0 plus 0 is equal to lambda 0 plus lambda 0. And we're still in a group. We can cancel one of the lambda zeros and we get that lambda times 0 is a 0 vector. Now, that means that if you multiply by 0 scalar any vector, or if you multiply using any scalar the 0 vector, you get 0 either way. Right? We are not going to prove a converse to this. If you have a product of a scalar by a vector, which is 0, the scalar is 0 or the vector is 0. So let us be given an x in V, a vector x, and a scalar lambda, such that lambda times x is 0. And let's assume that the scalar lambda is not 0. Then we can rewrite x as 1 times x. This is the last compatibility condition in the definition of a vector space. But then 1 is 1 over lambda times lambda, or if you prefer, lambda inverse times lambda. But I can use one of the compatibility conditions, so 1 over lambda times x can be rewritten by moving the parenthesis to the right. Now lambda times x I assume is 0. So I end up with 1 over lambda times the vector 0, and we just started the theorem by proving that this is automatically 0. So x has to be 0 if ever lambda is not, but the product lambda x is 0. And this concludes, of course, the proof of this little property. So we have seen what a vector space is, and we have seen that it has some basic algebraic properties that are reasonably intuitive. We have seen quite a few examples of vector spaces. Our next step will be to define the morphisms between those vector spaces. They are called the linear maps. Those are very, very important for our course because linear algebra, to a large degree, is actually the study of linear maps.